Hi, thank you very much for the opportunity to talk to you today about the SCEC community stress model. Before I get going, I want to acknowledge that the community stress model is really very much a group effort, and I want to acknowledge all the people who are listed here on the CSM website. All of these people were really major contributors to making the community stress model happen. So the community stress model is one of SCEC's many community models, often referred to as CXMs. Each of these CXMs has its own webpage where you can find the model and information about the model. The community stress model is at scec.org/research/CSM. So the point of the CSM is to develop models of stress and stressing rate in the Southern California lithosphere. The CSM is different from some of the other community stress models in that we haven't tried to build a single preferred community consensus model. Instead, we've been working on compiling multiple existing models of stress and stressing rate in Southern California. While we do have multiple models, they all fall into two general classes of models. The first is the stress models, and the second is the stressing rate models. The stress models are models of stress tensor in the crust and lithosphere, and these are mainly derived from inversion of earthquake focal mechanisms. We do have one model that includes the effect of topography, that is, how much stress do you need to support the topography we know exists. And there are also a couple of models that are based on physical modeling of the tectonic loading of the fault system that model in a forward way what you would expect the stress to be given all the assumptions of that physical model. The good news is that all of these models, even though they're based on really different data and assumptions and methodologies, come up with really very similar stress orientations across most of Southern California. Although they do not agree so well in the stress amplitude, which is something I'm going to discuss a little bit later. And also a caveat, if you are interested in stress amplitude, that the models that are based solely on focal mechanism inversion can't actually constrain the absolute stress. So the second sort of model is the stressing rate model. This is a model of how the stress tensor evolves through time. Most of these models are based on geodetic data, and most of them are based on models of that geodetic data, for example, block models. We include the USER-3 deformation models, and these models strain rates have been translated into stressing rate. There's also a couple of physical models of tectonic loading. Again, in this class of model, the implications of these models for the stressing rate. The good news with these models is that they are generally quite similar, especially near the major faults, although there are some differences that come from different modeling choices, such as choices of what secondary faults to model, choices of block boundary, and choices of locking depth. So the caveat with these models, however, is most of them are based on primarily on GPS data, which mainly constrains horizontal motion, and therefore these stress models mainly constrain the horizontal stressing rate. So what do these models look like? This is looking at the stress models, and here I'm looking at the orientations. Because the orientations of all of the models are so similar, I've just averaged them all together to show you kind of a representative model. And I've taken a depth slice at 5 kilometers depth. So on the left is the orientation of SH max, which is the maximum horizontal compressive stress direction. So it's well known that in Southern California, this SH max direction, that is the maximum compression direction, is pretty much north-south. It's slightly east of north. And that's what we see in green here over much of Southern California. Although we can see that there are areas where the stress is significantly rotated from that up to maybe about 30 degrees, either clockwise or counterclockwise. On the right, we see the stress regime. And again, we know that Southern California is mostly in a strike slip stress regime, and that's what's shown here in the green areas. In the orange colors, that indicates reverse faulting regime, and we see that, for instance, through the transverse ranges. And in blue is a normal faulting regime, for instance, in the southernmost Sierra Nevada. So these orientations are pretty similar for all of the different models. Each of the models covers maybe a slightly different geographic region and has differences in the resolution in various parts of the models. But in general, the stress orientations are very similar to what you see here. The stress amplitudes are a different story. Constraining the amplitude of stress at seismogenic depths is actually a long-standing difficult problem. And this dates at least from the 1960s and what was called then the San Andreas heat flow paradox. And that paradox is basically the question of whether or not differential stress at seismogenic depths is high, meaning on the order of hundreds of megapascals, as would be implied from laboratory experiments of rock strength. Or is the differential stress at seismogenic depths low, that is tens of megapascals, more on the order of an earthquake stress drop, as implied by the lack of heat flow anomaly along major faults such as the San Andreas? So unfortunately, the community stress model hasn't solved this important long-standing problem. There are different models in the CSM that have taken different approaches and end up with different answers as to what the absolute stress is. And that's shown here in this figure, which is a plot of differential stress versus depth. And these are two different models. And in the solid lines is showing the mean differential stress amplitude over the whole Southern California region. And the dashed lines show bound 95% of the differential stress values over the region. The model in red is a model that's based on what stress is needed to support the topography. And the blue model is a physical model of the loading of the fault system. And you can see that these models disagree as to the amplitude of the differential stress at seismogenic depths. And their averages disagree by even an order of magnitude at some depths. So unfortunately, this problem of the absolute stress amplitude hasn't been solved. So if you're looking for absolute stress amplitudes for your modeling, I suggest that you look very carefully at the model you choose, the assumptions of that model, and whether or not those assumptions are consistent with other assumptions in your modeling, so that you make a good choice of the right model that's right for your modeling, because we really don't have a community consensus to tell you what absolute stress amplitudes you should use. So looking at the stressing rate models, as I mentioned before, these are mainly models of the horizontal stressing rate. So that's what I've shown here. On the left is just the absolute value of that stressing rate. And surprisingly, it's highest along the major faults of the San Andreas fault system. And on the right is the SH max of that stressing rate. And as you can see, again, it's pretty much north-south compression as we would expect for Southern California. All right, so that was a little tour of the models. Now, how would you actually access these models and use them in your dynamic rupture modeling? Well, all of the models are individually publicly available on the CSM website. They're all in the same format as a text file, and all of them define stress on the same regular grid. So if you want to see the format of the models, you can just click on this link that I've circled here, the CSM model formats, and that will take you to a detailed description of the formats. And to get to the models themselves, you need to keep scrolling down on this page. And first you'll find the multiple stress models. As I've mentioned, many of them are from focal mechanisms. One includes topography and a couple are physics-based. And they all have little descriptions that can help you choose the model that you think would be the appropriate model for your purposes. If you click on the name of each of the model, it will take you to a page that has a summary of the model and some metadata for that model. That looks like something like this. At the top, there's some maps where you can see the spatial extent of the model, stress orientation, stress regime, etc. There's a short description of the methodology. There's contact information for the individual group who submitted this particular model. And if the model has been published, there are references that explain the model. And if you click over here on the right in the download, then you can download the actual data file for each model. If you keep scrolling down, then you get to the stressing rate models. And as I mentioned, many are based on geodetic data. Some include geologic and other data. Some are physics-based, and 3 of them are from the use of 3 deformation models. Again, if you click on the name of the model, that will take you to summary information and metadata for each model. And if you click the download on the right, you can download the models, noting that 2 of the models aren't ready for public download yet. So I hope this little tour of the community stress model has given you what you need to find what you need to start using these models in your dynamic rupture modeling. The stress and stressing rate models, their metadata, file formats, and all of that is publicly available here on the SCEC website. Again, that's scec.org/research/CSM. If you have any questions at all about the community stress model, please feel free to contact me. My email address is up here. And also, each of the models includes the contact information for the modeler who contributed that model. And so if you have detailed or technical questions about any model, you should go ahead and feel free to contact those modelers who contributed those models. So again, thank you very much for letting me talk to you today about the community stress model, and I'd be happy to answer any of your questions.